let's talk about balancing chemical equations. So we need to understand, what am I referring to with balancing chemical equations? I'm talking about finding ways to make chemical equations accurately represent the reality of what is happening in a situation. So before we do that, we need some vocabulary, because there is this word reactants and another term products that we use to describe portions of a chemical reaction. So we need to understand that when we talk about reactants, we're talking about the stuff that the reaction begins with, as in the things that go into the chemical reaction. They're always written to the left side of the arrow. The arrow, which is also referred to as the yield sign, yield means produce, points toward the things that are made by the reaction, which is the products. So the products are always written to the right side of the arrow. The reactants are always written on the left side of the arrow. And the arrow always points from reactants toward the products. So, having said that, I need to point out a couple other things. A chemical reaction, in addition to telling you what is consumed and what is made, may sometimes also include these symbols inside parentheses to the lower right of the symbol for the element or for the compound. And what they tell you is something that we're going to call a physical state. So what is a physical state? It's not necessarily a state of matter that's related to that. It just tells you whether it's solid, liquid, or a gas, or this aqueous, yes, that's pronounced aqueous, means it's dissolved in water. And although this isn't technically a state of matter, what it is it's a very important form that a lot of matter takes that matters to us a lot in chemistry. So that's why we look at this and say solid sodium reacts with aqueous, that means dissolved in water, hydrochloric acid, to produce hydrogen gas and sodium chloride dissolved in water, aqueous sodium chloride. All right, so that's something else to be aware of also. You should be able to do something like that with this also. Solid potassium and liquid water react to produce hydrogen gas and potassium hydroxide dissolved in water. All right, more things to point out, Actually, yes, I'll put all that up. So balancing chemical equations, in addition to showing you the state of matter and to showing you what's produced and what's required for the reaction, we also have to consider that a reaction needs to accurately represent what is being consumed and what is being produced, and how much of what's being consumed and how much of what's being produced. So this is pointing out an issue if you don't write a chemical equation right. Because there's this thing called the law of conservation of mass that we mentioned at the beginning of the school year. And matter can neither be created nor destroyed. So we have to consider that if you look at a chemical equation, we understand that CH4 represents a molecule with 1 carbon and 4 hydrogen atoms. Or 1O2 represents a molecule composed of 2 oxygen atoms. So if we look at that, we can say that in the reactant side there is 1 carbon and 4 hydrogens. That's where this comes from. And on the reactant side there's also 2 oxygen atoms. Okay, so we're referring to 1 carbon atom, 4 hydrogen atoms, and 2 oxygen atoms on the reactant side. If you take this equation literally and you count what's there, 1 carbon on the product side, 3 oxygens on the product side, and 2 hydrogens on the product side. If you take this literally, it says you start with 1 carbon, you end with 1 carbon. You start with 4 hydrogens, you end with 2 hydrogens. You start with 2 oxygens and end with 3 oxygens. So if you took it literally, it would be telling you that you had 2 hydrogens disappear and 1 oxygen appear, which is not going to happen because the mass of 2 hydrogens is far less than the mass of 1 single oxygen. It's like saying you had 2 mice disappear and an elephant appeared. So since that's not possible, if you take it literally, then it would be a violation of the law of conservation of mass, because you've had stuff disappear and appear, and you can't do that. Conservation of mass says if you start with a certain number of atoms, you need to end with a certain number of atoms, because a chemical equation is just rearranging the atoms in a molecule. That's all it is. You're not creating or destroying any in a purely chemical reaction. So we say, not that the reaction is wrong. It's not wrong. But we say it's unbalanced, because the thing is, if you do a test, this is like methane. It's natural gas. When it reacts with oxygen, that's called setting it on fire. So setting methane on fire really does produce carbon dioxide and really does produce water. So this is not a lie. The problem is, we need to look at a way to write this to make this balance but still show the same chemicals, because of the fact that this really is true. You can do a test and prove that carbon dioxide and water really are made when you burn these two chemicals, as in like reacting with each other. So how do we do that? Well, first of all, the process of doing that is called balancing the reaction. Let's consider how to do that. So this is that exact same equation written again. So balancing chemical equations, how can we make it work? We need to adjust some numbers in here, but not just any numbers. You cannot change these subscripts because you can't change the formula of the chemical. All right, in the lab we can prove that this reacts with this to make this and this. That is true. So H2O and H3O are not the same thing, or CO2 and CO or CO3 are not the same thing. So leave the subscripts alone. Okay, because the lab results show this chemical equation is right. So if you change the chemical formula, you're representing some other chemical, and that's not what's there. So in addition to that, you also need to consider, though, that you can change the coefficient. Now, what do I mean by coefficient? Let me show you. Okay, so we have to understand right now it's saying one of these molecules plus one of these makes one of these and one of these. But what if instead of just one of these plus one of these makes one of these and one of these, what if we put a number 2 right here? That's what this is. This is the coefficient, by the way. This is a coefficient, the big number. What if we put that in there? Now we're saying one of these plus one of these makes one of these and 2 of these. So we're not changing the chemical equation at all. We're still saying water. We're just saying 2 waters instead of 1 water. If you did that and you counted it up, you could say 1 carbon, 4 hydrogen. 2 times 2 is 4 hydrogen. Okay, look at that. 2 times 2 is 4 hydrogen. Distributive property, like in math. 2 oxygen. 2, and then this is 2 oxygens, not 1, because 2 times 1 is 2 oxygens. So 2 plus 2 is 4 oxygens. Okay, so you could do that, and what you get is you have the carbons balanced on each side, you have the hydrogens balanced on each side, but the oxygens, that's not balanced yet. So we're going to take that same approach and add another coefficient because it's not balanced yet. Okay, as it says here, not balanced, and this is the issue. So what do you need in order to balance it? This is just the same thing repeated from before. So it's just the same. And what we're going to do is say, okay, so putting a 2 here fixed that because we doubled the amount of each of these. So what do we need more of? We're short on oxygen, so we need some more oxygen here. So what if instead of 1 oxygen molecule, you had 2 oxygen molecules? Well, if you did that, then you'd have 1 carbon, 4 hydrogens, and 4 oxygens on this side, and 1 carbon, 2 plus 2 is 4 oxygens, and 2 times 2 is 4 hydrogens. So you'd have 4 hydrogens, 4 oxygens on this side too. So you would now have the exact same number of each element on each side, and that, we call it a balanced equation. So this we would be happy with as our final answer. All right, so this is what you would want. So let's look at some more examples of this. All right, so consider the reaction of ammonia and oxygen at 1,000 degrees Celsius. So there's ammonia plus oxygen reacting at 1,000 degrees Celsius to make these 2 things right here. We've got to go through the same process once again. So I will point out there's a little helpful hint that can go with this. I'll even write it on here because I definitely want people to remember this. All right, we want to save the pure element for last. Now, I took the time to write that out because that is actually a helpful hint for whenever you balance these things. Save the pure element for last because just like, and we actually did that last time. With oxygen was the last thing I balanced, like the pure element. Remember, a pure element is something that has only 1 kind of atom in it. So this is pure because it's only oxygen atoms. All right, so how can we go about doing this? I'm going to show you like the step-by-step on here. So we could say, oh, well, actually, you know, I'm going to back up a sec on this one. How do I know how to do this? So what am I doing? I'm just going to start at the beginning. So I see 1 nitrogen and 1 nitrogen right here. So that's good. So I'll move on to the next element. Hydrogen. There's 3 here and 2 here. So how did I know to do this? My little trick is when you have like 3 of one and 2 of the other, or like you have one subscript of one and the other subscript for the other, switch the subscripts. Like put this subscript right here, so that's where this 2 came from. It came from this H had a 2 on it, so I put the 2 right there. This H has a 3 on it, so I put it with the other H. And it turns out 2 times 3 is 6 hydrogens. 2 times 3 is 6 hydrogens. It works. It's a nice little trick, okay? So if you have, again, if you have 3 of this element and 2 of this element, you just switch them. And you can, if it was like 3 and 4 or 5 and 6 or whatever, you could do the same thing. You just switch them. It's a quick way to get the same number of each. Okay, so now I had 1 nitrogen, I had an unbalanced number of hydrogens, so I fixed it. So now I've balanced the hydrogen, 6 hydrogen, but by fixing the hydrogen, I broke the nitrogen. Now I have 2 nitrogens on this side and 1 nitrogen on this side. So what are you gonna do? Well, the easiest one is to times this nitrogen by 2. If I put this coefficient 2 in here, now I fix the problem caused by putting this 2 right here. Now I've got 2 nitrogens in the beginning and 2 nitrogens in the end, in the products. So what have I got so far? 2 nitrogen, 6 hydrogen, 6 hydrogens. So far, so good. Now we've done everything except for oxygen. How many oxygens do I have? This is 2 oxygen. This is 3 oxygen. So 2 oxygen plus 3 oxygen equals 5 oxygen. So 5 oxygens here. I have 2 oxygens here. How do I get 5 oxygens? Okay, I have to think, how do I get 5 oxygens? Well, if I have 1 of these, that's 2 oxygens. If I have 2 of these, that's 4 oxygens. If I have 3 of these, that's 6 oxygens. So 2 of these molecules is too few, 3 of these molecules is too many. So I need something in between. So what am I going to do? Here, there's a couple different ways I can approach that. I can just say, if I had 2.5 of these, that would make 5 oxygens. Or I could say, I need 5 oxygens. Each molecule has 2. So I need 5 halves, and 5 divided by 2 is 2.5 oxygens. So this is what I need. We call this a fractional coefficient. You're not allowed to have this in your final equation, so we're not done yet. But if I could have 5 halves, or aka 2.5 oxygen molecules, I would have 5 oxygens, because 2.5 times 2 is 5 oxygens to balance the 5 oxygens here. So, oh sigh, if only I could have 2.5 oxygen molecules. I could have 5 oxygens on the beginning, 5 oxygens in the end, and be done. But you've never seen a chemical equation that has 2.5 of something or 3.5 of something. Or like I said, you could have said, I need 5 oxygens, there's 2 in each molecule, so 5 halves oxygens. So you can either write 2.5 or 5 halves, I don't care, it's the same thing. So what are you gonna do at this point? The answer is, okay, find the number that makes it so that it balances, and then you're going to times this entire equation by a number in order to make it work. So what do I mean by that? I'm going to try timesing this entire equation by 2. So if I times everything by 2, this means this times 2 is 4, this times 2 is 5, this times 2 is 4, this times 2 is 6. I multiplied it by 2 and it gave whole numbers. If timesing this by 2 didn't give a whole number, I would try timesing it by 3. If timesing it by 3 didn't work, I would try timesing it by 4. If multiplying it by 4 didn't work, I would multiply it by 5, and so on until something finally gives whole numbers for everything. So that's what I do here. Turns out timesing everything by 2, I'll even emphasize, times 2, so that's what 2 times 2 is 4, 2 times 2.5 is 5, 2 times 2 is 4, 2 times 3 is 6. That's where all this came from. And then, is it done? Well, you don't need to ask the teacher, you don't need to Google it, you don't need to check the answer key, you can figure it out for yourself. 4 nitrogens, okay, that's good. 4 times 3 is 12 hydrogens, and 6 times 2 is 12 hydrogens, so 12 hydrogens, that's also good. Next, 5 times 2 is 10 oxygens, so 4 oxygens here, so 4 oxygens, and then 6 oxygens. So we have 10 oxygens here, and these add up to 10 oxygens here. So we've found that for each element, the number of elements on the reactant side is equal to that number of that element on the product side. So that's how we know we're good, and that's how we know that this works. All right, so then what you saw was called a fractional coefficient. You can either use a decimal or a fraction, but it gets the same idea. If I had said 5 halves, by the way, then when I times it by 2, 2 times 5 halves is, of course, 5, and you get the exact same thing. So it doesn't really matter how you do it. So we can look at other examples and get the same kind of idea. So go ahead, those of you who are watching this, pause the video. This actually works very similarly to the last. Try this one out, and then when you are done, go ahead and look at what I do and see if you got the same. Pause now. All right, so if you did it, you started by counting up your elements, and we usually just start here on the left, and so, okay, carbons first. I see 3 carbons here, 1 carbon here. Okay, let's balance up by putting a 3. Okay, that's good so far. So 3 carbons, 3 carbons. Cool. Hydrogen. That was next. Okay. Remember, got to count this one too. So that's not 7 hydrogens. There's 8 hydrogens here. So we need to make 8 hydrogens here. So the way we do that is put a 4. All right, so what's that done so far? 3 carbon, 3 carbon. 8 hydrogen, 8 hydrogen. So far, so good. 2 oxygen. And then, let's see, 3 times 2 is 6 oxygen, plus 4 plus 0 is 4 oxygen. All right, that is going to add up to 10 oxygens. All right, so I think I earlier accidentally said 2 oxygens. I take that back. 3 oxygens. My mistake. So everything is good now except for oxygen. We've got to figure out how to make this work with the oxygen. So, how are we going to make this work? All right, consider this. There's 10 oxygens on this side. We could try multiplying this by something, but if we change this, then we got to change our carbon, and we change our hydrogen, which changes the oxygens, which makes us change this again, and whatever. So that's going to open a really bad mess we don't want to deal with. So we're going to use this. That way when we change the number of this, we're only affecting oxygen and not carbon or hydrogen. So, 10 oxygens. So what if we had 2 of these? That'd be 4 oxygens plus 1 more is 5. Okay, that's not enough. What if we had 3 of these? That'd be 6 oxygens plus 1 more is 7. Okay, we're getting closer. 4 of these makes 8 plus 1 more is 9. Okay, there'd be 9 oxygens and 10. That's not enough. What if we had 5 of these? That'd be 10 plus 1 is 11. So we would have 11 here, which is too much. So 5 O2s gives too many oxygens. 4 O2s doesn't give enough. What do we do? All right, we have to do this. We're going to say we need 10 oxygens here. We already have 1 here, so we need 9 more. So I'm going to say, what do I need to get 9? I need 9 oxygens more. I'm going to divide by how many there are, so 9 halves. Or you could also say, and by the way, if you take 9 divided by 2 in your calculator, that equals 4.5. So I could also just put 4.5 right here. 4.5 O2s would give 9 oxygens here, plus 1 more makes 10, and that would balance this out right here. All right, so that's how we go about doing that, is we have to say, all right, find a number we can times this by so that the number of oxygens on the reactant side is equal to the number of oxygens on the product side. So again, you can either do that by being, okay, we need 10 oxygens. Here's 1, which means we need 9 more. So you can either say, oh, okay, well, 4.5 of these makes 9. Or you can say, I need 9. Each molecule has 2, so I need 9 halves of this. Okay, because 9 halves is 4.5. It's the same thing. All right, now, hopefully, at this point, it becomes clear you cannot have this in your final answer. So if you ever have a fraction or a decimal or whatever, you got to times it by whatever it takes to take a whole number. Try timesing it all by 2. If that doesn't work, times it by 3. If that doesn't work, times it by 4, and keep on going until you find one that does work. So we start by multiplying it by 2, and we see if that works. So 2C3H7OH plus 9O2 makes, times, don't forget, times this by 2. 6CO2 plus 8H2O. So when we do that, what we can check for is to make sure, did that balance right? Okay, because again, this is the result of times everything by 2. So 2 times 3 is 6 carbon. 6 carbon, that's good. Don't forget, this is 8 hydrogen, not 7. So 2 times 8 is 16 hydrogen. So we have 16 hydrogen here. Look, we have 16 hydrogen here. Okay, that part's good too. Finally, oxygen. We have 2 oxygens here. And then 9 times 2 is 18 oxygens. So 2 plus 18 is 20 oxygens. And then you do the same thing here. Do we have 20 oxygens on this side? 6 times 2 is 12 oxygen. And then 8 times 1 is 8 oxygen for a total of 20. So we do indeed have 20 oxygen on the reactant side and 20 oxygen on the product side. That means we have equal numbers of each element on each side, and we would call this correctly balanced. Right now, this is what it looks like on the animation on the PowerPoint slides. So you can see it shows the same process that I just went through. Again, saving the pure element for last, because that makes it easier to handle that last little bit at the end. All right, so final one to balance. What about polyatomic ions? So here's the thing. If you have a polyatomic ion present, and I see 2, I see carbonate and nitrate, this can actually, there is a way to simplify the balancing of this, and simplification obviously is a good thing. So here's the thing. You'll notice for one of these polyatomic ions, it's present in its same form as NO3 on the reactants and product side both. On the other hand, carbonate, unlike this nitrate, carbonate is not present on both sides. I mean, there's a carbon, there's oxygen, but CO3 on this side is not accompanied by another CO3 on this side. So here's what that means. For polyatomic ions that are present on both sides, you don't need to break it down and count how many nitrogens, how many oxygens. You can just say, oh look, a nitrate, 3 nitrates. On the other hand, if it is broken up, as in like carbonate here, but there's no carbonates anywhere over here, then yeah, you do have to count how many carbons, how many oxygens, and do all the balancing in that business. So let's look at how you go about doing this one. And in fact, you know what? Let's start with, well, the way we usually do. Let's start with the first one there on the left. There's 2 aluminums here, 1 aluminum here. We need to fix that, so we will. There you go, I just added a 2. So 2 aluminums, 2 aluminums. That does change other stuff though. So see this carbonate? We could go balancing the carbons, and that is a possibility. There's 3 carbons here. And there is 9 oxygens. But you'll notice, like, see these 9 oxygens? Do you balance this to get 9, or do you balance this to get 9? The answer is that's complicated, so we're going to save that till the end and let that most complicated thing take care of itself. I want to point out something else, though, before we get too much further. Check out the fact that this nitrate, there was 3 until we times it by 2, so now it's 3 nitrates times 2 is 6 nitrates. If we put this 6 here, now we have 6 nitrates on this side. And then 6 hydrogens. We need to make this have 6 hydrogens. So I'll put a 3 here. That way it's 6 hydrogens here and 6 hydrogens here. Note something just happened. I've done the aluminums. I did the carbons. I saved the oxygen for later, but I did the hydrogens and I did the nitrates. So I've done everything except oxygen. Oxygen is the last thing to do, but check out what happened. After I adjusted all this other stuff, I did count 9 oxygens here, and look at what happened. 3 times 2, because I adjusted this for the carbon back here, so I now have 3 of these, so 3 times 2 is 6 oxygens, and then I adjusted this to make the hydrogens work, and that made 3 oxygens for a total of 9 oxygens. So that thing earlier, I said that oxygen would be complicated, I said save it for later. This is why, because by balancing all the other stuff, the oxygen problem took care of itself, and we have it already set. So by doing that, look at what I've done. 2 aluminum, 2 aluminum. 3 carbon, 3 carbon. 9 oxygen, 9 oxygen. Now wait, remember, I didn't count this as part of the oxygen because when you count it as nitrate, you don't count it again. Okay, so 9 oxygen, I exclude that because it's part of the nitrate. So 9 oxygen, 9 oxygen. 6 hydrogen, 6 hydrogen. 6 nitrate, 6 nitrate. So going through things one at a time, I have checked that everything balances out, and this is a correctly balanced equation. All right, now, let me show you guys how that would look. This is an alternative way of looking at it, and here I did it slightly differently, but it got to the same thing where I did the aluminum first, and then I did the, the nitrate next, balancing the nitrates, and then I did the hydrogens and then the carbons. And at the end, like I said, I saved the oxygen for the last, and that complicated problem took care of itself. And I point this out for good reasons, because you'll notice when I solved it myself, I did a slightly different order than this, but it worked out in the end. So if properly done, there are oftentimes different ways to balance things, like you can do this one first, then this one, and then this one next, or you can do this one first, then this one next, or whatever it is. And as long as you're keeping track of things carefully, you'll get there. All right, so there we go, ladies and gentlemen, another example of balancing chemical equations.